Hello, this is my presentation of the final results of the project for the Cardano blockchain in the Fund 3 called Write Apps as Continuous Workflows. This project is intended to solve a problem very common in current web application, but much more acute in smart contracts and in general blockchain application, and is the proliferation of endpoints, both in the website to connect microservices, and also endpoints in the with the blockchain as such, so that the program becomes a sort of spaghetti of handlers for endpoints with blocks of code with no logical intuitive relation between them. This makes very difficult to maintain, to verify, especially verify and develop any further, because this lack of expressiveness of the code. The answer to this problem is to develop a way to express all the flow, all the execution flow, including the multi-user workflow, which is a smart contract at last, as a single sequence of steps, so that the specification and the flow match one-to-one, so that verifiers and people with no knowledge of Haskell can see the flow very much in the code, despite that the small details are not understandable. This facilitates a lot the management of the code for improvements and for verification and anything related. So the strongest problem of expressing a multi-user workflow smart contract this way is the very strong requirement that the program should support stops and restart from cold restarts, because workflows and in general and in particular smart contracts last for a long time, including years. So even years. So the program is lives. The program execution lives for more than even the mean time between failures. So this is very hard to achieve, and also programs regularly are stopped and restarted for improvements, for maintenance, for scalability. Even machines are stopped. So this is a requirement to take into account. Another good requirement is to allow fast testing, so that the program can run as in console mode, as well as a microservice server. So the initial code for a example smart contract is this simple game that it was the sample in the first iterations of the Bluetooth applications, It's just a game in which one user put money in a number and blocks it in the blockchain, and any other user can enter and guess the number and get the money if he guess well the number. The pseudocode, the initial pseudocode that I propose for this small contract, including the chain code of the small contract, is this sequence in which basically we see the sequence of actions. One user enter the amount to log, the blockchains receive the amount and look it in with the number considered. Then any other user enter in the middle of the workflow, so this endpoint is public, and execute the guess option, and in this case the guessing token is a string instead of a number, and if the result is correct, the user receives the money. This is the top level of this description of this game, and the project intended to write it at this level, to write a program at this level. Let's look at the final aspect, how it looks in the real code. This is the guess game finally, or most likely like the guess game in real terms, using the library that I developed. First, these games do not contain the blockchain code. It's only contain the HTTP, the web endpoints. Later I will show you blockchain endpoints, but this is for the sake of clarity and execution, intended to show you how the sequencing works. Basically, the program asks for login data, which is in this case is the name and the wallet number, to the user by a web request or a console request. Then it has the option to play the guess game or auction game. The auction is not implemented, but it appears here in order to show that we can compose different elements of different microservices or features using this operator. We will see later how this means in the execution code. Once the user chooses the guess game, this is the endpoint that initializes the guess game. He can look a number to guess it, to initiate a new game, or it can guess other games created by other users with different numbers. And the step in which the user guess is here. Guess of the user which entered the game, so that they can the program output if the result was right or not. The program display the user enter the guess number, the user display the log number, the user that chooses the guest number, and if it is success or not. Let's look at the program and execute it. So this is the program as it appears at the beginning. You see that there is a set of console options. We can see all the options. There are many related with other aspects of the program, but what we are interested in are the endpoints. To see the endpoint, we execute this command, and we see that the only endpoint available is this, because this is the one that appears at the beginning of the program. We will execute. What we see with this menu option is a display of how to call the endpoint. Okay, so we can invoke the endpoint both with a web request, also with a console request. We can write this and we can enter here the user and the wallet. Let's do it by web request. Okay, so let's execute it with rectifier of the JSON response. Oh, sorry. Maybe some, okay. Here, there is a backslash here, a lot. Okay, this is the response. What we see are two options. The two composite option with this operator. One is for the guess game, another for the option. The JSON and URL was composed by the first with this statement, and the other is the option input section that appears here. We choose the first one. It has no parameters. And the question is, because it's this statement is local number to guess it. So we enter one number. There is as you can see, there is a variable here, which is the number to enter, 42. And we see what the response is to guess the number I just entered. But the nice of the game is to all of other users to guess that number. That's why this endpoint is public, so other users can enter and see at this moment the published games that they are parameterized by the name of the user. So we enter as another user, to invoke the first endpoint, again with other parameters. And we see the two options, guess game and option. We execute. Well, we can even, well, let's do again this, and we choose the guess game. And now we have two instead of one responses. The first is the opportunity to create a new game or to guess the number entered by the previous user, the game that initiated the other user. So we can play this with we publish it, the first game, and the second user now see this game that is open. We can even stop the program, save the state of the execution. We can save periodically, but I have it, in this case I save it manually, but this is not a problem if we want to do it automatically. If we restart the program, we can execute any of these endpoints. So we execute the guess game for the user, for the first user, 42. Okay, so we see that the program executed. It recovered the state necessary to answer the endpoint, which was not in execution, and immediately created the response. The result is what we expected. The entire number 42, the log user, first log user, the guess user, and the result is true. We can try another number and say that result is false. Note that session data works by using this kind of primitives, in which we can store any kind of state data, which is work across different users, so that the program remember the session state for the user that is running at this moment. And you say that the program executes even if the start from cold. We can use IPFS to store session data, so that the program is completely free from databases, from local databases. We can even execute in a machine and restart in another, so that the program recover the state. And even it can work with many machines, writing to IPFS. This is very good. I developed an interface from the internal database of the program in memory database with IPFS. The program also can persist in any kind of database, in Oracle, MySQL, anything can store session data. more. Another thing is that the publish and the public and published primitives. One, as you might understand, the public publish endpoints, and the published display those endpoints and at a certain point in the execution. This published is like a wormhole, so that when the user press a published endpoint, the execution continuing in the point that correspond to this the execution point where corresponding to this endpoint where it was published. This concerning HTTP endpoints. We have here a version of the log guess game, the same game, using the testnet. In this case, we have the code is slightly different. There is no auction, and after the gateway wallet, there is execution of the game sequence, and in this case, the guess game are published with this string, but basically is the same. The game sequence is a log followed with a guess. The guess is published, but in this case there is a blockchain endpoint. The blockchain endpoint is an invocation, in this case, of the log primitive, the log birth created in the guess game Haskell code as it was defined in the examples of the Bluetooth apps. Is an early example from 1 year ago. Now there is, I think that it is not available in the Bluetooth apps latest versions, but the code is exactly the same that appear in the sample. We only program the top level of the workflow. We use the endpoints created as such, and the code created in the sample. The result is a clear specification of the program. RAM-PIV is a primitive that I created. It's not a RAM-PIV of the core. There is a RAM-PIV defined in Bluetooth PIV core, but it's not the one that I defined. RAM-PIV is defined in my library. It's defined as this, and if you like to know, it is too low level, but it's in some parts of the in the library. Anyway, what it does is to execute PIV code in the PIV monad, so that we can execute whatever code the PIV has is necessary. In this case, the PIV chunks are the ones defined in other parts of the samples, so that we draw this code from the sample from the PIV examples and put it at the right place. This is the sequential version. Not interesting. And this more or less everything related with PIV endpoints. We has a pass through a a way to invoke PAV code, and we can use any PAV code here, so that we have the best of both worlds, the low level of the PAV and the high level of the workflow execution sequences. The bad thing, the problem is that PAV code is evolving very fast, and in general the blockchain code, the Haskell blockchain code is evolving, and especially there's a periodic release of new networks, and this is made it difficult to cope with adapting new versions to the library. We will see the Uniswap code adapt for my library, in which basically it performed the Uniswap. You can see the Uniswap description in any a standard blockchain application, in which smart contract, in which users can swap coins without a central authority or a personal authority. It's just using the program algorithm. But basically the program start a factory, which is the basic structure in which put pools of pairs of coins to exchange. Once the factory is created, any user can enter in the application and either create a new pool, remove it after that, or swap money in a created pool, in a published pool, or in both directions, or execute endpoint on the swap kind, because it's this one, etc. Once the flow is defined, we can have the code of each one of these chunk of code. Factory created, for example, is just the same code that was defined for this functionality in the standard example of the blockchain of the Plutus app. So there is no invention of new low-level PAV code. We invoke the same endpoints and the same logic for waiting for a state, etc. These primitives change slightly between releases. By the way, this is the execution of the program in a new thread, so that this primitive, this code execute in parallel with this other. By the way, the original code of the Uniswap have two bugs that prevent from executing this example. Anyway, as you see here, the core functionality is independent of the PAV or any other mechanism for calling the blockchain. we can use the PAV or block frost or any other interface with the blockchain. Block frost has been very successful because it hides the complexities and the changes in the Haskell code of the blockchain for the wallet and for the smart contract, the Bluetooth core. So this is much more preferred than the PAV. But in the future, maybe soon, the PAV will be mature enough to use it as such. Anyway, you can say that the flow is easy to, at least I think, is easy to understand and easy to program at the top level, so that you can play with it and make application and give me feedback and improvement points. As I said, the program can respond and execute the program in console mode, so that we can enter the same input that the program will expect from a post request or a GET request. And that's almost all. I hope that you appreciate the utility of this kind of approach to creation of multi-user workflows and smart contracts. The multi-user nature of smart contracts make it mandatory to execution in server side, and this is, I think, this is a good way to represent a small contract to create a complete blockchain application. So that is, for this moment, the overview of what I did. So thank you very much, and I expect your feedback if you like.